Okay, today we're going to talk about inverses of matrices and matrix equations. We've been exploring in Gauss-Jordan elimination, and we talked about triangular and reduced row echelon form so that we could see our solution with the identity matrix on the left and the solution set in that far right-hand column. So let's talk about inverses now. Consider, if you will, that we have an equation like ax equals b, and in order to solve that equation for x, we would multiply both sides of the equation by the multiplicative inverse of a. That is a inverse. As long as it's not zero, we can do this. So it's this general idea that's similar to matrix equations. Only instead of lowercase letters, we want to call our matrices with capital letters, as we've seen in the past. And if you have a square n by n matrix and you see A inverse, that's how we read that notation, where matrix A times its inverse is equivalent to its inverse times matrix A, and those products give you the identity matrix, then you know the inverse, A inverse, is called the matrix. In short, easier to understand terms, that is this way. If you multiply two matrices together, A times B or B times A, and in either case or in both cases your product is the identity, then you know that those matrices are inverses of each other. So whether you understand it better this way or this way, we're talking about inverses. So first let's experiment to show that if we multiply A times B, we're going to produce the identity matrix, and likewise B times A. So this is what we ended up with our last lesson. We're going to multiply row of A times the column of B, and we've got 1 times -5, so that's -5, and 2 times 3, so that's our first element, A times B. Then going over to column 2, we have 1 times 2, and we're going to add 2 times -1. Then moving our highlighted portions to row 2, column 1, we have 3 times -5, so -15 plus 15. And then our last multiplication with row 2, column 2, we have 3 times 2 and 5 times -1. So you can see that A times B is going to give us 1 here, 0 here, 0 here, and 1 here. So A times B does give us the identity matrix. Now we're going to do the same thing, only this time we're going to multiply B times A. So we want to multiply backwards. So row B times column A is going to be -5 times 1 and 2 times 3. So in B times A, we've got -5 plus 6. Then moving our column over, that gives us -10 plus 10. And then going to row 2, column 1, that's going to give us 3 minus 3, and row 2, column 2, that's going to give us 6 minus 5. So in the same exercise, we have 1, 0, 0, 1. So to formally clean that up, we know that A times B and B times A both give us the identity. So B is the inverse of A. And that's how we check for inverses. Now, how do you go about finding an inverse matrix? So we're going to see a couple of different approaches here. A matrix is called invertible or non-singular if the matrix has an inverse. Otherwise, we call that matrix singular if there is no inverse. And a non-square matrix cannot have an inverse. Not all square matrices have inverses, though. But if a matrix does have an inverse, then the inverse is unique. Also, if matrix A is order m by n, and matrix B is order n by m, and the row is not the same as the column, then those products are going to be different orders and they can't be equal to each other. So here's how you find an inverse. I'm going to model it for you instead of just reading it for you. So here we have matrix A, and I want to set up an equation. A times a variable matrix is going to give me the identity. So I need a variable matrix, and I'm going to label them X with row 1, column 1, X with row 1, column 2, X with row 2, column 1, and X with row 2, column 2. So this matrix A times my variable matrix has to give me 1, 0, 0, 1. It has to give me the identity matrix. Okay? So if we employ that row by column approach to this left side for A times X, then we're going to see that we have something we can solve. So 3x sub 11 plus 2x sub 21, and moving this over, 3x sub 12 plus 2x sub 22, and then going down to row 2, back to column 1, that's x sub 11 minus x sub 21, and then over to column 2, that's x sub 12 minus x sub 22. So this is our product matrix, and that has to be equal to the identity matrix. Now, if you look carefully, you can see that we have a system of equations here. So we've got 3x sub 11 plus 2x sub 21. That has to be equal to 1. And we have x sub 11 minus x sub 21, and that has to be equal to 0. So in that first column, we have them equal to this column. And likewise in the second column, we need 3x sub 12 and 2x sub 22 to equal 0, while x sub 12 minus x sub 22 must be equal to 1. So we have two systems. And if you just treat them that way, by adding this system, let's see, we want to get rid of the x sub 21s. Or you could do substitution and say x sub 11 is equivalent to x sub 21. Let's do it that way. X sub 11 is x sub 21. So by back substitution, we could say 3x sub 11 plus 2x sub 11 is equal to 1. So 5x sub 11 is 1. Okay, so in the second one, we have this second equation is equal to 1. So we could say x sub 12 is equal to x sub 22 plus 1. So replacing x sub 12 with x sub 22 plus 1 plus 2x sub 22, we would have 3x sub 22 plus 3 plus 2x sub 22 is 0. So 5x sub 22 is equal to negative 3. Now we want to solve for, let's see, we know x sub 11 is 1/5, and x sub 21 is also 1/5. And we know x sub 22 is negative 3/5. So if x sub 22 plus 1 is x sub 12, then x sub 12 has to be equal to 2/5. So we have our four values. So the inverse is going to be row 1, column 1, row 1, column 2, row 2, column 1, and row 2, column 2. And it's also common for us to take out that factor of 1/5 and just have the matrix part be integers here with the scalar out in front. So either way is appropriate, this way or this way. So here's another way to find an inverse of a 2x2 matrix. So this first way was with matrix equations. The second way is just a formula that we memorize because we're going to talk about the determinant. The determinant is A times D minus C times B. So we're going to take the product here and the product here and subtract them. Write that over 1, and that's the 1 divided by the determinant. And then here in the formula, we're going to interchange the A and the D, but we're going to keep B and C in their current location and put a negative on both of those, or do the opposite of both of those. So using that approach here, we can get the inverse. Remember, it's 1 over the determinant, which is AD minus BC. And we're going to switch the location of A and D and put D up here and A here. But we're keeping the sign on B and C. We're doing the opposite sign on B and C. So we've got 1 times 4 minus 3 times negative 2. And then the 4 and the 1 change places. The opposite of negative 2 is positive 2, and the opposite of 3 is negative 3. The determinant looks like 1 over 10 and 4, 2, negative 3, 1. So this is our inverse matrix. This is the inverse matrix. So that's using the formula for a 2x2 matrix. Now, this example, we're going to use a calculator. So I have calculator directions. On my calculator, I want to create this, and I'm using modeling with a TI Inspire. That's what my students have. So if I want to find the matrix for A, I'm going to use the template, which is on the keypad. And if we open up my matrix, my calculator, hold on, give me a minute. So looking on my calculator here, I'm going to find that I use the scratch pad, and down here at that location, you can see how the matrix pops up, and the matrix is right here. So we can use that. You can also do, another option is to do in the scratch pad, menu 7, I want to create number 1, a matrix number 1, and then I can do the same thing. I can say I want a 3-row matrix, and I want a 3-column matrix, so I've got a 3x3 matrix, and we can do that approach as well. So once you have that set up, then you're going to enter those numbers into each of the element boxes that you see pop up. And these were the elements. Now what I did is I found that I just used the inverse key, but you can also have the calculator if you wanted to. So if we go back and say menu 7, a matrix, And once I set that, then I'm going to use the up arrow and the -1 for the power to be the inverse of that matrix. So using that up arrow and the -1 for the inverse, then pressing enter, it's going to tell me what my inverse is here. And here's the property. If we want to solve a system using inverse matrices, this is the procedure for using a matrix equation, where we have a matrix A times a variable matrix, and that's going to give me matrix B. And if we multiply both sides by the inverse of A, then A times its inverse is equal to identity, and then we'll know the variable matrix. So that's our process. We want to give that a try here. So remember, my goal is to write a matrix equation with matrix A times a variable matrix, and that's going to give me my solution set here. So first we start out with the coefficients. That's 3 and -1, -2 and 1. So I've got my coefficient matrix. I'm going to multiply that by my variable matrix, x times y, and that's going to be equivalent to my solution matrix for 5. Okay, so I want to find the inverse, because the procedure said I want to multiply left and right by the inverse of matrix A. So the inverse of matrix A was 1 over the determinant, so that's 3 times 1 minus -2 times 1. Interchange the D and the A, change the sign on B and change the sign on C. So we're looking for the inverse matrix. We're going to multiply that times the matrix 3, -1, -1, 1, and the variable matrix, and we're going to multiply this side times the inverse matrix, which is what? 1, 1, 2, 3 times the solution. So this matrix times this matrix is the identity. And we're not going to spend time doing that. We just know that that's, if we've done the work correctly, that's the correct answer. And then we want to multiply the row times the column and add those together. So this row, 4 plus 5, and then go to row 2, since the other one is only one column, and that would be 8 plus 15. So our matrix equation, that gives me the solutions for x and y, because this matrix times xy is just going to be xy, will be 9 and 23. So using that approach of matrix equations, we found out that our solution set for those two lines intersect at the point 9, 23. So our solution set is 9, 23, either by this matrix or by the ordered pair. And then our last example is a free response type question. We have to set up a matrix equation. So we know the hourly cost of a security company to guard a warehouse and outside fenced area depends on the hourly cost X in dollars of using a security guard and the hourly salary Y of using a canine companion. So the cost for 3 security guards and 2 canine companions is $285. So that would be our first equation. 3 security guards and 2 canine companions will cost us $285 to guard that warehouse. But the hourly cost for a team of 4 security guards with 4 canine companions is $480. So what does our matrix equation look like? 3, 2, 4, 4. Then our variable matrix, x, y, and then our solution, 285 and 480. So we know if we multiply the inverse times this matrix, it's going to give us the identity. But if we do that, we also have to multiply the right side by our solution matrix. So I want to find the inverse matrix. So the inverse matrix is 1 over 3 times 4, that's 12, minus 2 times 4, that's 8. So that's 1/4. And then the D and the A interchange, and we use the opposite sign on B and the opposite sign on C. So this is going to be our inverse matrix. This is our inverse matrix. So I'm just kind of doing a little scratch work here. So what does this turn out to be? 1/4 of 4. So our inverse matrix is 1 and negative 2 over 4. So negative 1/2. And then negative 4 over 4, that's negative 1. And the last term is 3 over 4. So this is our inverse matrix times 3, 2, 4, 4 times our variable matrix. These two are the identity, so we end up with our variable matrix. And then on this side, you can't put the inverse matrix over here. It has to go in front. 1, negative 1, negative 1/2, 3/4. And then we're multiplying that by 285 and 480. So we're doing the row by the column. So this is easy. I'm not going to get the highlighters. We've got 285 times 1. And we're going to subtract 1/2 of 480. And then on the y, the row times the column, we have negative 285. And then 3/4 of 480. So that's, let's see, 4 goes into 480, 120 times, and 120 times 3, that's 360. So I don't have to use my calculator. And then we know the cost for each one of those components. So 285 minus 40 is $45 for each security card and $75 for each canine companion. And you may want to write that in a sentence so it makes sense to the context of the problem. A security guard will cost us $45 an hour, and the canine companion will cost us $75 per hour. Okay? So that's the end of lesson 5.